Hello, everyone. As we know, the pre-trained language models have achieved state-of-art results in many natural language processing tasks. BERT is one of the most prominent pre-trained language models due to its effectiveness and universal usability. However, the online deployment of BERT is often blocked by its large-scale parameters and high computational cost. Hence, we propose the towards non-task-specific distillation of BERT while sentence representation approximation. My presentation will be in 4 parts. Firstly, I'm going to talk about the motivation of work. Next, I'm going to talk about the methods. Then, the experiments will be shown. Finally, I will conclude our work. Recently, the emergence of pre-trained language models has brought natural language processing to a new era. The contextual representation by ML, GPT, BERT, and some other pre-trained language models are shown to bring large improvements to many tasks. However, these pre-trained language models usually consist of at least hundreds or millions of parameters. Developing with deeper network design and more effective training methods, pre-trained models' performance improves continuously. At the same time, the number of parameters of pre-trained language models increase largely as well. This picture vividly shows the parameter size of pre-trained language models. These powerful pre-trained language models hold a huge amount of parameters, leading to the difficulty of conducting online deployment. To address this issue, diverse distilling methods have been proposed to compress BERT and meanwhile keep its semantic modeling capability. Some typical distilling methods are listed in this table. Soon compress BERT into few layers by shortening the distance of internal representation between student and teacher BERTs. For the sentence pair modeling, Barkan found the cross-attention functions is consuming and tried to remove it with distillation on sentence pair task. Tang proposed to simulate BERT with a much smaller bias team on specific tasks, and then Han introduced some data augmentation methods to further improve the performance. However, such distilling methods might capture task-specified biases for the current method, highly rely on a label datasets upon a specific task. This indicates that the powerful generation nature of BERT tends to be lost in the compressed model. Meanwhile, manual labeling is a high-cost work, and large amounts of annotated data cannot be guaranteed to obtain. Thus, it is necessary to compress BERT with a long task-specific training procedure on unlabeled datasets. Now, I'd like to talk about our proposed method. To achieve the non-task-specific distillation for BERT, we propose to approximate sentence representation by minimizing the cosine distance between the sentence representation given by the teacher network and the student network. As shown in the figure, we take the BERT as teacher model, and the D-dimensional vector C is extracted from the top transformer layer upon the CLS token. For the student model, our bias TM is employed to enclose the sentence into a fixed-size vector. After that, a fully collected layer without bias term is built upon the bias TM layer to map the vector into a D-dimensional representation. Then overall, we propose an adjusted cosine similarity between the two real value vectors to perform the sentence representation approximation. On the one hand, the choice of this distillation objective is due with the unnormalized sentence representation extracted from BERT. And on the other hand, studies have shown that it is meaningful to compute the cosine similarity between sentence embeddings given by BERT. Since the distilling strategy purely focuses on the simulation of sentence embeddings for BERT, similar to BERT, the student network can also perform transfer learning to any sentence level downstream tasks, such as text classification and sentence matching. The left part illustrates the model architecture for single sentence classifications. The right part shows the model architecture for sentence pair tasks. Well, to evaluate the performance of proposed non-task-specific distilling method, we conduct experiments on the 4 tasks from the glue benchmark. The SST2 task is to predict the binary statement of a given single sentence. The QQP task is to determine whether each pair is semantically equivalent. The third one is similar to the QQP task, whose dataset consists of sentence pairs with binary labels denoting their semantic equivalence. The next one is a crowdsourced collection of sentence pairs with textual entailment annotations. This table shows the results of our proposed model and the baselines on 4 datasets. Let's divide into 4 groups, including the base models without distillation, distilled models using structure, distilled by STM, and the last group shows the influence of the data augmentation. Firstly, we can see our model performs on par with AMO on all tasks. Furthermore, as shown in the number 14, fine-tuning on a specific data with augmented data helps our student model outperform the AMO baseline. Such fact shows our compressed BERT can provide a good pre-trained representation of AMO on the sentence level task. Comparing row 12 and 10, row 14 and 13, we can observe that our model consistently outperforms bias KD on all tasks, no matter with or without data augmentation. To further evaluate the distillation effectiveness, we also report each distillation method's improvement upon the corresponding student directly treated without distillation. It can be observed that our method, SRA, improves the scores by over 3.9% on average, while PKD and KD only provide less than 1.2% increase. And our distillation can further cooperate with task-specific distillation and data augmentation. To compare the inference speeds of different models, we also implement experiments on 100,000 samples from the QQP dataset. The numbers of parameters reported in the data exclude those from the embedding layers, since such components don't affect the inference speed and are related to the vocabulary sizes. It can be observed that the BISTM-based distilled models have fewer parameters than BERT, AMO, as well as other transformer-based models. Compared to the next model, both the BERT-based and AMO are around 20 times larger in parameter size and 20 times slower in inference speed. Even the smallest transformer-based model, BERT PKD, is also 4 times larger than our proposed BISTM SRA. Since pre-trained models have well-initialized parameters, these models usually converge faster and less depend on large-scale annotations. As shown in this table, we're experimenting training the models using different proportions of the dataset. No doubt, all the models can achieve better results using more training data, while BERT performs the best. Comparing with the pure BISTM models, the non-distillation-based models slightly improve the performance by around 2%, while our model outperforms other BISTM models trained with 20% and 13% data respectively. Besides, similar to BERT, the difference of accuracy between BISTM SRA trained with 20% and the one using 100% corpus is relatively small. This phenomenon indicates that our model converges faster and is less dependent on the amount of training data for downstream tasks. Such conclusions are also reflected in the comparison in the figure or model's learning curves. Despite the task-specific data, Wikipedia corpus is used in the distillation procedure or proposed method. We also train different BISTM SRA-based model using 1 to 4 million Wikipedia data, and the corresponding fine-tuning performances are reported in this table. Different from the fact that the more training data has a significant benefit in particular task, 4 times the distilling data can only improve around 0.5 points on the 2 tasks. Besides, we conduct the comparison among models by directly extracting their sentence values without fine-tuning upon sentence similarity tasks. It should be noted that in this table, AMO, BERT-based, and introduced as a comparison basis, since it can give the state-of-the-art untuned sentence representation for the similarity measurement. It can be seen that our model outperforms the BISTM KD on the matrix. Besides, we can also observe that for sentence similarity quantification, I arrange the context-worthy balance of the sentence representations works better than taking the final hidden state corresponding to the CLS token. From the experimental results, the following conclusions can be drawn. Firstly, for a specific task, our proposed dissemination method can bring the 5% improvement to the pure BISTM model on average. Secondly, the proposed model can outperform the state-of-art BISTM-based pre-trained models. Finally, compared to the task-specific dissemination, our distilled model is less dependent on the corpus size or downstream task with satisfying performances guaranteed. Thanks for listening.